Three stars, tracing this glowing figure eight, chasing each other forever along a single curve. Three bodies pulled only by gravity almost never do anything this tidy, they usually tumble into chaos. This is one of the rare exceptions, a perfect, repeating dance.
Three stars on one looping path, on purpose?
Not on purpose, it's a knife-edge solution, balanced just so. And it isn't the only one. Start them differently and you find other dances, triangles, rosettes, whole families of them. Let's see why three bodies are usually chaos, and how these dances slip through. Two bodies under gravity are easy, they trace a clean, repeating ellipse, worked out exactly with pen and paper. Add a third, and that neat solution falls apart, there's no general formula for three bodies. Almost any starting arrangement just tumbles along, never settling into a simple repeating path.
So 2 is solvable, but 3 breaks it?
Right, 3 or more is generally chaos, with no tidy answer. Yet hidden in that chaos are special arrangements that do repeat exact periodic dances. Some chase each other along one shared curve, like the figure eight. Others hold a spinning formation, a triangle or a rosette. Mathematicians have now found hundreds of these three-body dances, and even ones for 4, 5, and more bodies.
So order does exist inside the chaos, you just have to find it?
Exactly, rare islands of perfect rhythm in a sea of tumbling. Back to one dance. Let's name what you're seeing. Each bright dot is a body, and the glowing curve is the path it keeps retracing, lap after lap. While the curve stays closed and clean, the dance is repeating. When it smears, order is breaking down.
So a crisp closed curve means it's still in step?
Yes, a clean curve is the dance holding, and a smear is chaos creeping in. These dances are balanced on a knife edge, watch what one tiny nudge does. We start on a perfect repeating orbit, and give one body the faintest push. For a while, it still looks like the dance. But the error grows, lap after lap, and the curve starts to wander. Soon the tidy path dissolves into a tangle, chaos.
So the dance only survives if it's exactly right?
Yes, for the fragile ones, a hair off and gravity tumbles them into chaos. So why are these dances so fragile, when a planet's orbit feels rock solid? Most of these solutions are unstable, any error pushes you further away, never back. And gravity has no friction to settle things down, so nothing pulls a drifting orbit back onto the dance.
So there's no groove for it to fall back into?
Right, the dance is a razor's edge, not a valley, miss it, and you're gone. But a few special spots are stable. Take a star with one planet circling it. 60 degrees ahead of the planet, and 60 behind, sit 2 points where gravity and the orbit's motion balance. The Lagrange points L4 and L5. Nudge a speck near them and it doesn't run away, it just loops slowly around the spot. Real asteroids gather there, the Trojans, thousands of them, sharing the planet's orbit.
So those 2 points are calm harbors in all the chaos?
Yes, stable enough that, over billions of years, whole crowds of rocks collect there. This isn't just math. Jupiter shepherds 2 great swarms of Trojan asteroids at its L4 and L5. Marching ahead of and behind it for billions of years. And telescopes like James Webb sit at a different Sun-Earth point, L2. Which isn't quite stable, so they nudge gently now and then to hold station.
So the stable spots in the three-body dance are real places we use?
Yes, calm islands, mapped by gravity, in a problem that's mostly chaos. So next time you picture 3 things pulled together by gravity, don't expect order. Expect tumbling, with a few rare, perfect dances and a couple of quiet harbors hidden inside the chaos.
Chaos almost everywhere, with islands of rhythm.
3 bodies, 1 law and a thin, beautiful thread of order.